Hello, everyone. My name is Xiaowei Dai. I will report our work on 3D animal pose estimation. Unsupervised 3D animal canonical pose estimation with geometric self-supervision. I will report from the following aspects. Animal pose estimation plays an essential role in various fields, such as animations, neuroscience, and bio-inspired robotics. However, little work has been devoted to 3D animal pose estimation. This can be attributed to data scarcity and the depth ambiguity inherent in 2D to 3D mapping. Recently, synthetic data and domain adaptation have been exploited to address data scarcity. However, these methods are aimed at 2D animal pose estimation. SMAIL is a statistical model based on 3D scanning of toy animals. The model requires 3D animal shapes to constrain the optimization process, which undoubtedly limits model generalization. This begs the question, can we estimate the 3D animal pose by leveraging only 2D data? Similar problems concerning human pose have been extensively studied, and this has inspired our work. According to different supervision, they can be classified into fully supervised, weakly supervised, and unsupervised. To address data scarcity, we propose an unsupervised method to estimate 3D animal pose, given only 2D poses. To deal with perspective ambiguities, we introduce a canonical consistency loss and a camera consistency loss to impose geometric priors in the training process. The mapping between 2D and 3D we simplify to the left figure. 2D pose can be obtained if the 3D pose is accessible. Conversely, the given 2D pose, the 3D pose is almost unknown. Fortunately, the following assumptions about mapping from 2D to 3D poses have been proved to be completely acceptable in practice. The same 3D pose can produce different 2D poses from different perspectives. Conversely, these different 2D poses should produce the same 3D pose. Based on the above assumptions, we propose an unsupervised 3D animal canonical pose estimation method with geometric self-supervision. The method flow is shown in the figure. The proposed network consists of 3 parts: the pose generator network, camera estimation network, and the 2D pose discriminator. Given a 2D pose, the pose generator network and camera network estimate 3D canonical pose and camera rotation respectively. During training, the synthesized 2D pose also regresses 3D canonical pose and camera rotation. We define self-consistency losses in both 3D canonical poses and camera rotations. Moreover, the networks are also trained by minimizing the reprojection error and limb symmetry loss, and discriminating the synthesized 2D poses from the real 2D poses. To validate the proposed method, we conduct evaluation experiments on the SMAIL and a China set datasets. We use the MPIP as the metric for evaluation. It can be seen, the proposed method significantly outperforms the unsupervised methods proposed. Specifically, our method outperforms the unsupervised method 9 by about 12.75% on the smell dataset. Compared with smell, we can observe that the performance of all methods on the China set decreases. The main reason for the performance degradation is the huge deformation, which makes the 3D pose estimation very challenging on the China set. In order to understand the impact of each constraint on the proposed method, we conduct ablation studies on various algorithmic components, and we evaluate these models on the smell and China set datasets. Among them, the gain component demonstrates the most significant of improvement, which suggests that without prior information about 2D pose to get the training, the synthesized 2D pose may severely deviate from any reasonable 2D pose, degrading the model greatly. The above results are obtained when ground truth 2D poses are available. We systematically evaluate the proposed method when the 2D poses are corrupted by different levels of noise. The increase of MPIP of our method is the lowest in all the cases. Qualitative results on the China set, as can be seen from the left figure. However, the animal has self-occlusions, or flip ambiguities in the viewing direction, as can be seen in the right figure. The proposed method performs unsatisfactorily in these samples. We introduce a canonical consistency loss and a camera consistency loss to incorporate geometric pairs that allow the network to learn in a self-supervised mode. The proposed method does not take into account constraining the torso and tail. We will consider this in future work. This paper assumes an orthogonal projection. Future work can consider more complex projections, which are more in line with the real world. All of the above. Thank you for listening.